Hey mathletes, in this video, what we're going to talk about is limits and how they relate to finding tangents. Okay, what does that even mean, right? What is he talking about this time? All right, here's what we're going to do. And this is a really, really, really important part of differential calculus. So let's look at a parabola from grade 11. If I want to know how fast this function is changing at a certain point, let's say just some random point right here, we'll call it x. This graph doesn't have a consistent slope like we had in grade 10. In grade 10, when we had a straight line, a linear, we were always able to find the slope. So guess what? What we're going to do is we're going to draw a straight line like that touches our graph at just one exact moment. That's called a tangent line. And by figuring out that tangent line, we're actually figuring out the instantaneous rate of change at that exact moment of x on this parabola. So this is actually a really, really big deal. Okay, so that's what we're going to do today. Now, one of the interesting things about calculus is that when, it was being discovered a few hundred years ago, before the days of the internet and Google, right? You had different people working on it at the same time, but pretty far apart. And when that was happening, they were coming up with different approaches to the exact same problem. And that's what we're going to see today. We're going to find this question, determine the equation of the tangent line to the curve in two different ways. The first way was our good old friend, Sir Isaac Newton. So Sir Isaac Newton thought of it like this. He developed the Newtonian method, which is this. He said the limit as x approaches a of f at x minus f at a over x minus a. Okay, so what he's saying here is this. Let's go back to our parabola. He's saying we're going to find the limit at some point A, and we're going to move closer and closer to it. So as x gets closer to A, that's what he's saying. Okay. And what we'll see in the second method is the same idea, but they do it just a little bit different. Okay, so the limit as x approaches A. Well, what is A? A is the point we're approaching. So that's A right here. So this is the limit as x approaches 2 of f at x. Well, that's our function. So x squared plus 4x minus 3 minus f at a. Well, a is 2 over x minus a. So x minus 2. Then once we've got that figured out, it's all just algebra. And that's why people like this. So you go the limit as x approaches 2 of x squared plus 4x minus 3. Well, f at 2, well, guess what? F at 2 is just our y value sitting right here. So minus 9 over x minus 2. Okay, now we're good to go. We just keep simplifying. You must write the limit as x approaches 2 all the way down the page until we do our substitution. 4x minus 12 over x minus 2. Okay, I tried direct substitution, so guess what? I get division by 0. So what did we learn earlier? If direct substitution fails, we will do some factoring, right? So x plus 6, x minus 2 over x minus 2. Hey, look at that. Those two factors divide out. I'm going to come up here. That's equal to the limit as x approaches 2 of x plus 6. And now we can do direct substitution. 2 plus 6 is 8. Okay, but what does all of this mean? What we just found, my friends, is actually the slope of that tangent line. This is the slope all the way along, but only at that one instant. So this is the slope when x is 2. Now, we want the actual equation of this tangent line. So here's what we have. There's several different ways to write the equation of the line. We could use y is equal to mx plus b. That was the one we used a lot in grade 10, but the one I prefer is point slope form. We didn't use it as much in grade 10, but it's real easy. So look at, I know a point. It was the point 29. So there's my y. There's my x, the point 29. And what did I just figure out? The slope was 8. There is the equation of the tangent line. Now, if we want, we could then rearrange this thing and write it in different forms. So if I add the 9 over, guess what? There's our favorite friend from grade 10, mx plus b. Or if you're looking in the solutions in a lot of textbooks, they'll write it like this in general form. All 3 of those are correct answers, but they certainly look different, don't they? Okay, so this is called the Newtonian method. So what you really, really want to know is this right here. Okay, so Newton thought of it as a point A, and we're using our x values to approach that point, right? Okay, so one way to think of it. But somewhere far away was another person working on it. And how they were thinking of it was the same idea, but just in a slightly different way, right? So again, we've got ourselves some parabola. And I know the parabola I'm drawing doesn't match the parabola in the question. Doesn't matter. Okay, what they said was this. Okay, here's a point A again. And then what they said was, we're going to move closer and closer to A, but we're going to call it over here. And I'm going to call this point A plus H. And I'm going to say what happens as we make H smaller and smaller and smaller as H goes towards 0. So as H goes towards 0, this point that's away from A will move towards A. Okay? So a different way to think of it. Here's what they said. They said the limit as H approaches 0 of a point f at A plus H minus f at A all divided by H, just like that. Okay, so this one's called first principles. And with a name like that, you know it's important. We'll use it a little bit more than we'll use the Newtonian method, but they're both equally valid. Okay, so what we're going to do here is then we're going to the limit as H approaches 0 of f at A plus H. Okay, what was our function again? Our function was x squared plus 4x minus 3. So f at x is equal to x squared plus 4x minus 3, and we had the point 2, 9. So what we say then is A is still 2. So it's equal to the limit as H approaches 0 of 2 plus H minus f at 2 over H. All right. Then what we do is now we're going to do some composition. So we'll sub that back into our function. So f at 2 plus H. So I get 2 plus H squared plus 4 times 2 plus H minus 3, and then minus f at 2. Well, f at 2 is 9 all over H. Now that I've done that, I always try direct substitution. But if I try direct substitution, I'm going to get division by 0, and that's a problem. So I have to try something. The thing I'm going to try is, let's try to simplify that numerator and see what happens. So what am I going to get? I'm going to go 2 plus H times 2 plus H. So I'm going to get 4 plus 4h plus h squared plus 8 plus 4h minus 3 minus 9 over h. Okay, didn't help me out yet. Didn't get rid of that h in the denominator, right? So let's keep going. Let's just simplify. Well, h squared. Now let's look at our h's. Well, 4h and 4h, those cancel. That's nice. We got rid of our h squared already. And then what else do we have left here? I've got 12. And I've got 4 plus 8 is 12 minus 12 over h. And that's not going to help me because now I'm not able to simplify. So did I make a small mistake somewhere, friends? H squared. Oh, yeah, I made a mistake. Why did I cancel my h's? See, I knew I did something wrong. 4h plus 4h is 8h. Come on, bad teacher, right? I'm sure some of you are screaming at the screen right there. Don't cancel those. They add together. Okay, and now what I notice here is I've totally screwed this up. This is minus 12 plus 12, which is 0. Maybe I need another coffee, hey? Look at that. Those two go to 0. Well, now what can we do in our numerator? Let's factor out an h. Like that. What happens? The two h's divide out. There goes our division by 0 problem. Now we let h be 0, and what do we get? 8. Wait a minute. Isn't that the exact same thing we got right here? The slope is the same. It's just a different way to do it. So again, this is us finding the slope of this tangent line at the exact moment when x is 2. Okay, that is when x is 2. And now, friends, that we have that slope, we could go back if we wanted to and find the equation of that line in point slope form. So when we're using either of these two methods, when we use either the Newtonian method, which is the limit as x approaches a of f at x minus f at a over x minus a, or we use first principles, which is the limit as h approaches 0 of f at a plus h minus f at a over h. What we're doing is we are finding the slope at the exact instant of whatever x value we're looking at. Okay, the slope will change for everywhere else on the graph. So we're finding the slope at that exact instant, at that exact moment. That is incredibly, incredibly important. So there it is. Those are your two methods. I need you to get good at both of them, and you'll get more, you'll like one more than the other, but I need you to be able to use both. Okay, my friends, I hope that helps find the equation of a tangent line.